Well, here we are back with these two characters again. We've got our very, very fast train with our Hawaiian shirted observer in the train, and we've got our observer on the platform. We've also set up our light clock. Our light clock, before we were running vertically, this time we're going to run it horizontally. So what happens is the light clock sends out a pulse of light. The pulse of light travels forward to the front of the carriage, reflects off a mirror, then bounces back to the light clock where it hits the sensor, which gives off a beep and then would send out another pulse of time, a pulse. And that gives us a way of measuring time, a clock based upon light. And remember, we're working through the implications of Einstein's assumption that the speed of light is constant for all observers. And we've already discovered that things that appear to be simultaneous aren't necessarily so, and also that time is dilated, that people will see a moving clock running slow. Okay, well, let's think about this in the point of view of the observer inside our train here. And we'll run the clock, and you can see that it takes 29 time intervals for that pulse of light to move to the front of the carriage and back to the rear of the carriage. Well, let's have a look at it from the point of view of the person on the platform now, as the train moves by at around about half of the speed of light. So let's have a look at how our clock runs. Okay, well, we're already up to 29 time intervals, and the light pulse isn't anywhere near getting back to the back of the carriage. So what's going on here? Now, if you're clever, you'll remember that the clock, according to this observer, the clock on the train is running slow. In other words, when he saw the person in the train measure 29 time intervals, he'll say, aha, yes, but your clock is running slow. So if someone measured something as 5 minutes and their stopwatch was running slow, you would say it actually took longer than 5 minutes because your clock is running slow. And if we do the maths, and you can do that, go back and look at the other video, you find that instead of 29 time intervals, this observer here is expecting that event to take place in 34 time intervals. So all is well if the light pulse gets back by 34 time intervals. But it doesn't. What's going on here? It's taken 39 time intervals. Well, think about speed, distance and time. They're the only things that we can change. The speed is the speed of the light pulse. Well, we're going to assume that everyone sees that at c, the speed of light, so we can't change that. Time, well, we've already just changed time. We've allowed for the fact that time is dilated and it should get back in 34 time intervals rather than the 29 that the observer in the train thinks. It still doesn't work, so there's only one thing left for us to vary, and that is the distance. That's the length of the train, the distance that our light beam has to travel. We actually have to make the train shorter, because as the front of the train is running away from the light pulse, it's going to take it longer and longer to get there, the faster and faster the relative motion of the train is. So what we have to do is we have to adjust the length. We have to shrink the train, compress the train in the dimensions. You notice the height didn't compress, only the length. It's getting squished down in the direction of motion of travel, and let's have a look at how that plays out. The front of the carriage is running away from the light pulse, but because it's not so far away now, the light pulse is able to get back in our 34 time intervals. So everybody agrees. So isn't that weird? Here's another implication of Einstein's assumption, that the length of something moving relative to you is going to contract, and the faster that you go, the more that length has to contract, because the faster the front of the carriage is running away from the light beam. And so we have to shrink the carriage in ever-increasing amounts to make sure that the light beam can get back there in time. And here when we run about 75% of the speed of light, it bounces off, it just kind of gets back there in the expected 44 intervals of time. And if we go very, very fast, then we're going to have to really shrink it. And as we approach the speed of light, the length of that object is going to shrink. And of course, like everything else in special relativity, this is a perfect mirror of itself. So the person in the carriage doesn't see their carriage shrinking. What they do is they look out the window and they see the platform shrinking, because it doesn't matter who's moving. So the person in the carriage sees the platform contract in length, the person on the platform sees the train contract in length. And that's one of the other implications of Einstein's assumption. In the next video, we'll look at the mathematics behind that.